1.6 is about so more on linear equation systems and invertible matrices, but the heavy lifting has been done. But keep in mind, in the moment with what we have here from inverse matrix, everything is square. The question is still, what about non-square matrices? I mean, the Gauss algorithm tells us a lot, but it turns out for this, we really need chapter 4 in our book. At the end of chapter 4, the non-square matrices will be clear, no? Non-square linear equation system. In the moment, once we concentrate on the inverse, everything is about square matrices. Okay, so, and like I said, this is just now a sequence of results, and there are consequences out of inverses and matrix vector multiplications. So we have a linear equation system, A times X equal to B. Then it has 0, also no, 1, or infinity, and it was based on the picture in 2 dimensions. But now we have all the tools available to do this in general. In order to show this, turns out it's pretty easy just by using matrix multiplications. What is clear is the number of solutions is either 0, 1, or more than 1. I mean, that's clear. What else should happen? No? So we know AX equal to B has, I write 0 again instead of no, has either 0, 1, or more than 1. That is clear from just counting. It has to be 0, 1, or more. When you look at the statement of our theorem, 0 is 0, 1 is 1. So what we have to show is if you have more than 1, you automatically have infinitely many. And then we are done. So assume A times X equal to B has 2 different solutions. And I call them X1 and X2. So these are 2 solutions and they're not the same. Then we calculate V equal to X2 minus X1. So that's also vector. Now we are looking what happens if you multiply A times the vector V. That is A times X2 minus X1. Then we learned matrix multiplication is distributive, so I can distribute my A. So this is A times X2 minus A times X1. But now what is actually AX2? Because it's a solution, AX2 is B. X1 is a solution, so A times X1 is also B. Turns out this is 0, and this here is a 0 vector. No, yeah. So that means this vector times A is 0. Is it possible that the vector is 0? No, because X1 and X2 are different. So this is not 0. So now we just take A times X1. I could have also picked actually X2 plus alpha V. Alpha can be any real number. We can do A times X1 plus A alpha V. Alpha is a real number, so this is X1. AX1 is B plus alpha A times V, but AV is 0. Alpha times 0 is 0, so we get B. And here again, alpha is in R. It can be any number in R. So therefore, X1 plus alpha V is a solution of Ax equal to B for every alpha, but there are infinitely many alphas, so we have infinitely many solutions. Okay, so this proved what we did, what I mentioned to you in the first day of class, which we saw in a special 2x2 example, that every linear equation system has either 0, 1, or infinitely many solutions. So in the moment you have two solutions, you find this vector v, which when you multiply by a, it just becomes a 0 vector. And that generates infinitely many solutions. And again, this is something which becomes clearer a little bit in more clear what the role of this v is. V is an example of a kernel or kernel vector. So something which is annihilated by A. Okay, so we finally have shown this in the general case. You can never have a linear equation system which has exactly two solutions.